Okay, welcome everyone to HAO Colloquium. Today, our speaker is BC Low from HAO. It is my great pleasure to introduce BC. BC received his PhD in 1972 from the University of Chicago. The late Gene Parker was his thesis advisor. After his year as research associate with Gene and another year as visiting scientist at HAO, BC went home to Singapore to manage building barges and tugboats in his parents' family shipyard. In 1979, BC returned to physics in the United States, spending a year as NRC Senior Research Associate with the late Einar Tannberg Hansen at NASA's Space Flight Center in Huntsville, Alabama. BC then joined HAO in 1981 as Scientist 1, became Senior Scientist in 1987, and retired in 2014 to take care of his Singapore family affairs. From 2017 to the present, scientific work brought BC back to HAO as a visiting retired scientist. He has published 180 papers on basic magnetohydrodynamics and solar magnetism. Today, BC will be speaking on the magnetic origin of the solar wind and CMEs.
Thank you, Masumi. Thank you for inviting me and all of you for coming. I have to say I'm very much out of touch to come to this colloquium without having given any in the past recent years. I mean, this whole thing is so new to me. So what I thought of talking about is to collect various corona processes I have worked on and others have, and give you a sort of a first principles narrative to run through the whole thing. And as I did this, I realized there was a remark that was passed around when I was a graduate student. It came from Enrico Fermi, who said that you mustn't forget how what a pleasure it is to listen to something familiar. and so many of the things that I talk about are familiar, so that is nice to be talking about. But when you put them together, certain things come out at you, and that is the part that motivated me to come here. And why did I think of this? I thought about this for several years. I was in contact with Jim Parker for his last 2 years when he was still alive. And we talk about various things. And then I got into this project with Scott McIntosh about certain things having to do with parcels of fluid in the interior that actually is a storage of vorticity and magnetic twist. So while I'm working on these, I kept thinking about how much do I really know or don't know about the corona. So I'm going to review how much I know or don't know. Okay, so the first slide will be, it's not working. What do I have to do? Oh. I have to go to maybe my PowerPoint. Yeah, it's working. So let me run, I hope, smoothly, and I get to the end where I want to be. So the open solar corona, the key word is open. It's really an open atmosphere. It's optically thin, 10 to the 33 x per second, I think, will get out clear through corona. It's million-degree hot, mainly fully ionized hydrogen, near perfect conductor of heat and electricity, and the global magnetic field, low beta 10 gauss at the base, and it suppresses cross-field electron thermal conduction, and that's crucial in what we are going to talk about. And that simply means the magnetic flux surfaces are almost a perfect insulator of heat. These two corona solar eclipse pictures are very outstanding. The one in 1980 is when the corona's polarity is reversing, and you don't see any hint of a dipole field, but you have this single remarkable units in the corona that you can identify. There's a helmet streamer arcade, so they tend to be long, and it's all around the sun. Then the other eclipse picture that I found terribly exciting is the one in 2020 when they actually captured a CMU just in the course of making its way out. And a thing of great interest in the talk is going to be the three-part helmet streamer. So if you look at the helmet streamer, say on the right, you see there's a shell, and then it is high density, it goes out into a streamer, and then under the shell is a cavity, low density, and then at the bottom of it resides a prominence. Okay. So to really look at that, we really got to think of CMU as episodic as opposed to the global solar wind, which is a constant ejection of mass out of the corona. And the review of Arthunhausen of the solar maximum emission CMUs is very remarkable because it is a full solar cycle of CMEs that he was able to have in his hands. There was a break in the interval from 1980 to 1984. For those of us who are old enough, that's when the instrument broke down, and there was a first, I think, space in repair of the instrument. Now, if you look at the Hundhausen's numbers, episodic CMEs at 10 to the 15 to the 16 grams, and something like 1 to 3 CME a day, you get 10 to the 11 grams per second, and that's only about 10% of the solar wind mass loss, which is about 10 to the 12 or 13 if you estimate it. And so it's just not that impressive as a mass loss. Okay. But every CME is a significant perturbation in the solar wind. And to lift 10 to the 15 grams or so out of the sun's gravitational potential, well, that is a lot of energy in the budget. And the last point is very interesting. CMEs have a broad range of speeds. It could be as low as 2 kilometers per second. I remember Arthunhausen laying on the table his coronagraph observation from the SMM instrument. And you look at it, there's a systematic of the expansion going out into the corona. So the speed is very broad. And to give some reference to the speed, the escape velocity where the CME takes off is about 550 kilometers per second. Okay. So now let me get down to the narrative. So let me run through a number of things. Why should there be a solar wind? Basic cause of a solar wind is simply that heat content actually gets spread by high temperature conduction along the field lines, if you like, as you go further out, and it overwhelms 1/r² gravity. And that's the reason for the solar wind expansion. But a hydrostatic calculation can actually tell you something fundamental about that. Can I stand up and talk? No. So let me quickly go through this business of the polytrope. A polytrope is that pressure is a power law in the density. S0 is like your entropy, so it's a constant. And your gamma is equal to 5, that's your monoatomic particles, and that is your adiabatic gas, okay, because you have all these particles, it's conserving entropy. But if you generalize the gamma to be a number, it could be larger than 5/3, smaller than 5/3. If it's larger than 5/3, that is very interesting because in an expansion, density goes down, and if it is smaller than 5/3, it doesn't go down as fast. Then the fluid is actually retaining its thermal energy, if you like, as it expands, much better than say polyionized hydrogen would be doing. And if you do a steady hydrostatic equilibrium equation, which is so easy to solve, you get a density distribution This is a first order ordinary differential equation, and therefore you will have a free parameter or constant of integration, and set that be R1, then the density has a distribution this way. It goes down at some value, and then it disappears at R equals to R1, and that's where you see the vacuum outside the atmosphere. And you can calculate the total mass in this hydrostatic atmosphere, and you find that it depends on R1. And the larger R1 is, as the further out it extends, the greater the total mass. Or if you turn it around, if the mass is as large as you want, then R1, the extent of the atmosphere, will go as far out as you need to account for the total mass. But that depends on the gamma, the polytropic index. So if gamma is this line. If gamma is greater than 4/3, closer to 5/3, for example, then you don't have very much energy as it expands in the gas. And therefore, the gas can expand as far out as you need to account for the M0. And as R1 goes to infinity, then the total mass also goes to infinity. And that's very kind of reasonable for a hydrostatic atmosphere. But if gamma is less than 3, and less than 4/3, and n is less than, what is n? N is just a redressing of that constant. Okay, then you discover that indeed the greater the mass you have in the atmosphere, the greater R1 would be. But as R1 goes to infinity, this total mass comes to a constant, which is very troublesome. In other words, if the boundary of R less than R sun is actually a rigid ball, nothing can get into it. And then if you chuck some mass into it, into the exterior, say that's your M initial. And if it exceeds this maximum for the sort of heated atmosphere, you can't find an equilibrium. And that's hardly surprising, because if you have excessive mass, it keeps extending further and further out. But the thermal energy doesn't go down very fast. So at some point, it overwhelms your gravity. And therefore, this amount of gas you chuck into outside a rigid sphere is going to expand outward, and the outer layer simply just go take away to infinity. And what's left behind is going to be a M0, which is below this, and that's how you get your hydrostatic equilibrium for a given mass, provided it is not too large enough. So we know already from the hydrostatic atmosphere, you can't just have a heated atmosphere and expect it to extend, out to infinity. So the next slide is where Jim Parker in the late 1950s decided for himself that the corona is actually expanding. So the best thing to do is to go pick up a model to look at what an expanding corona would look like. So you stay with your polytropic index, you still have your gamma. But now, instead of the force balance between pressure gradient supporting the mass, the weight of the gas, you have acceleration, a steady acceleration. And since you have a steady state, then you have a constant of the whole steady flow, which is your constant mass going through each radial distance out to infinity. Then this equation can be massaged into this other equation that tells you that in this equation, if your solution is going to extend to infinity, then these two quantities have to go to 0 at the same time, so that this down thing, the gradient of the velocity, remains finite. And it says simply that the point where it happens is that the fluid will go through the sound speed, and therefore it gets to be supersonic. And at some point in the flow, and if it's supersonic at some point in the flow, this must also disappear. And this is actually your escape velocity squared. So it would get supersonic at a point where the escape velocity is equal to the sound speed. And when you work out a solution, here is an example of a flow where where gamma has to be less than 3/2, then you get a flow outward. And here is your flow. So you have two parameters, F0, the mass flux, and the total energy in the flow. And if you plot it as a contour map, you've discovered there's this remarkable solution, this one that's going down, and this other one that's going up through a sonic point, and it goes to a steady flow. And that is the parameters for which you can get a steady flow out of you can't talk about the sun. This is the solution, so simple. Everything is coming up from a source at the origin and outward. And this is a sonic point. It is at this point where the velocity increasing and accelerating reaches supersonic point. And this is exactly where velocity is equal to the escape velocity. So there's something terribly interesting about it. You know, I'm an old guy. You know, when I first learned about this, I usually have very brilliant theorists arguing with me, but why should the solution know where to get to be supersonic? There's nothing mysterious about it. This wind is expanding. And if it is expanding, then the sound speed goes down. So at some point, the flow is going to be supersonic. So that is really the nature of it. It's just the expanded gas which defines the local sound speed and becomes supersonic at this point. But there's so much work done about this. But the one that really struck me was a study by Hauser and Lear. They were treating genuine explicit heating of the corona. So what did they do? They placed the location of the heating the addition at different radio distances all the way out. They discovered that if you are anxious to get a high terminal speed, okay, and you put too much heat down here, you only succeeded in expanding more gas from that local region into the flow. The terminal speed is always given by the total mass expelled divided by the total mass. So heating below the sonic point can only bring about a lowering of the terminal speed. To be able to heat your flow to high speed, you got to put your heat somewhere above eventual sonic point to be. Then what happens? And whatever you do up there, because they are in a supersonic region, no influence will ever come back to influence your lower part. And let's say something, and this is a point that I will be ending upon. We're so preoccupied with the sun, so solar wind. So down here, mass conservation says that your low corona, way below even your sonic point, is constantly heaving upward. And that is not part of our sort of a conscious thinking about the corona, I think. At least for me. But I realized finally, my God, when you look at a low corona, say your eclipse picture, in the low corona is heaving slowly, not perceptibly, until you get to somewhere around here. So this is a point that I would like to come back to later on. Then to keep a big picture in mind, let me pause to say the following. The temperature should be rising from 6,000 degrees at the photosphere through the chromosphere and transition region to 1,000,000 degree temperature in the corona. It's not a mystery. They keep saying it's a mystery. It's not a mystery. It's not a mystery for a gravitationally stratified atmosphere, heated everywhere, thermally conducting and cooling by optically thin radiation. That means the radiation does get out. So stratification simply means that lower down your density is higher and therefore they can emit better. Higher up, it's lower, they don't emit very well. So what do? You end up the upper part hotter, so that it drives the thermal flux downward to be radiated where the more dense atmosphere can radiate away. In fact, that's precisely what we have in the sun. Now, radiative cooling in the case of the corona, I'm talking about real physics now, not a polytropic gas. The radiative cooling has, the cool down time something like a fraction of a day. And the remarkable thing is that the corona is never seen to have collapsed into a chromospheric temperature. And not only you need heat to keep that going, but it should be noted that thermal conduction is practically shut off across few lines. So this heating has to be everywhere, because if you heat up a particular tube, then the sideways there's no exchange of thermal energy, and therefore single flux tubes will collapse. And finally, I should like to point out that this photosphere chromosphere and transition is really a complex boundary layer. It separates the interior of the sun through this boundary layer with the corona above. And it's just through this layer that magnetic flux emerges into the atmosphere. And it's a complex boundary layer in the sense that at the photospheric level, the magnetic field is actually, taking the form of vertical fibers of a kilogauss, almost scale height in its width. Another thing that I need to come back to first state, and then I don't have to come back to it. So these are the MHD equations, and then there's Lorentz force, pressure gradient, gravity, acceleration, and then you have your viscosity. In here, conservation of mass, and the induction equation where you have resistivity in there. And then this is your polytropic entropy, if you like, which has to be accounted for depending on how much non-ideal processes you have in the system. But any reasonable estimate of the resistivity for the magnetic field, as an example of how you might deal also with the viscosity, is that the Lundquist number, which gives you a measure of this diffusion of magnetic field, the Lundquist number is so large, so this is 1 over Lundquist number, that for most length scales, you find that it is negligible. In fact, I once estimated that even if you manage to get something which is around the mean free path of electrons in the corona, you find that resistivity is negligible. So by and large, magnetic fields are frozen into the plasma. And now I come back to the eclipse pictures, and I'm going to concentrate on the 3-part helmet streamer that I sketched over here. Okay. So there's several electric current sheets in this problem. So item number 1 is where the solar wind flow is taken. This is simplified. There's no rotation of the sun. So the wind simply just follows the field line outward. Okay. And it has a current sheet in the equator, because the bipolar field that got open will have to cross over this equator. And so there's a current sheet in the equator, the magnetic equator of the sun. And the solar wind is no longer simple. It's no longer a matter of the sound speed. There are all these hydromagnetic speeds as well as the Alfvén speed. So that's a complicated region where the wind is. Then the second sheet, current sheet, and that is the boundary between the wind, in the interior, between the helmet, the dense helmet, and the cavity. And the cavity can be interpreted to be a flux flow running, say, in this direction, because I'm assuming excess symmetry. So that is a current sheet where the field topologies are different and currents flows differently. And there's a sheet in there where the tangential discontinuity of the magnetic field is to be expected. And then there's a third one. The third one is this one. It separates the high density region from the wind. And then there is a fourth one, yes, right here. At the bottom of this closed field lines, which is the poloidal field of the flux was sticking out in azimuth direction, then there's a prominence sheet which is supported by the current sheet. There is a prominence in the form of a sheet that's supported by a sheet light current density. So with that, what can one say about it? First, we got to get away from the limitation of an axisymmetric global atmosphere. So I was very lucky. I can't remember what year this was. I was able to find a solution in which a magnetic field is supported by, in which the atmosphere in uniform gravity together with its pressure is supported by the Lorentz force of a complicated field. But to see how complicated it is, let me take the boundary distribution of this solution and calculate for its potential field, which is the simplest magnetic field could have. Then you have the usual streaming of potential field lines from the positive polarity on the surface to negative polarity crossing this so-called neutral line. But in this problem, with a sufficient heavy weight, this is uniform gravity, the magnetic field is no longer potential, and it actually there's a few lines that rise and twist many times before it finds the opposite foot point. Okay, and I remember how terribly exciting this was. I got this solution into closed form, and then when I start to integrate for the magnetic field, as I change parameters, suddenly the few lines starting from here, instead of looking for a nearest one, was wiggling its way in the screen, my goodness. So that was so exciting. So that was what the rope that you see in the axisymmetric picture would look like in three-dimensional geometry. And I'll have more to talk about this later on. But anyway, so this is just give us some idea about how a realistic geometry of a magnetic field would be. Now, a magnetic field lines that actually rises and go down and come back out again this way may be interpreted in many observations to be a twisted curve that actually has its central part coming through the photosphere and rising into the atmosphere. A helical field has a handedness. You follow the field and then you twist around. And so this is the positive handedness to that flux flow. If you take that flux or field line and reverse this direction, let me just change the direction, the handedness remains the same. So that's very pretty to think about. And there's a robust observation. Solar magnetic field have a hemispherical preference to be left-handed in the northern hemisphere and right-handed in the southern hemisphere. And because by the topological property that when you reverse the field line direction, you don't change the handedness. That preference actually persists from solar cycle to solar cycle with no change in the preference. In physics, anything that don't change is very useful, because then you begin to grab at something. Okay, and how do you know what the handedness was? It is the prominence people who discovered that. Leroy and Van Boerhaeuwen did a lot of work with that too. You can know the handedness because when you measure the vector magnetic field in a prominence sheet, you're looking at material sticking at the bottom of this U-shaped local U-shaped tubes. So you can measure the horizontal magnetic field, and then you can also look at where it is coming from, and you can determine the handedness. So that's how handedness was determined. Now, in hydromagnetic turbulence study. You can't prove this, but you could, if you wave your hand, but not too hard. You don't. Otherwise, you can't even convince yourself. But you could show that magnetic reconnection under conditions of very high Lundquist numbers, meaning resistivity is very small, and therefore reconnection takes place only in a small thin layer. Then you find that your magnetic field actually don't destroy the twist in it because everything took place in a very thin layer. So reconnection only transfer twist as opposed to destroying it in any significant amount. And then you have a real problem. If the handedness and the twist in each northern hemisphere and every solar cycle is not changing, and flux keep coming out, then you have a horrible situation of your unbounded accumulation of the handedness and therefore of magnetic field of the particular handedness. But every solar cycle, in general terms, don't show that kind of accumulation. And therefore, we have finally know how to think of CMEs. CME may not be significant as a mass loss, but it is very significant because it takes also a flux system out of the corona. And this is a bodily expulsion of a flux system. And therefore, a discrete flux system is actually permanently taken out of the corona. So you see, when I start to think like that, I realize that we learn a lot of things and become very familiar, but it is such remarks that can really turn you on. You see, a CME is not just expulsion of mass, but also expulsion of flux. But it is a flux system of a particular handedness so that you don't have this problem of overaccumulation of left-handed structures in the northern hemisphere and then right-handed in the southern hemisphere. But what is this darn thing twist? You got to find a way of quantifying it. Otherwise, what does it mean that you have an accumulation of left-handed structures? And helicity is the property of the magnetic field that is not destroyed when you reconnect under high Lundquist number conditions. And I am now going to digress and talk about helicity without going too far into it. So what is helicity? So mathematically, you could say helicity is a twist in the magnetic field that is shown over here, the interlinkage, the interlinking of, say, a pair of flux lines. Okay. If the magnetic field is wholly contained, meaning it is contained in a volume without threading across the boundary, then this helicity is actually very meaningful. That's a real problem. Once you introduce the vector potential, because the vector potential has a free gauge to it. And it's no good to have a property that depends on the gauge. But as long as your magnetic field is contained in a volume, not threading over the surface, and this, despite this arbitrariness of the gauge, is physically unique and it's meaningful because you can show it describes, say, two closed tubes of fluxes and how they're linked together. But the concept breaks down if you have a magnetic field that threads through the boundary, because then you can't follow field lines to its completeness to know that that's an integer number of times one field line is winding over another or a pair of linked fluxes. And this was really a conceptual crisis. And Michberger, this is his PhD thesis at Harvard, he found a way to resolve this problem. He has to deal with anchored magnetic fields, and you can't talk about linkages without tracing the full length of any magnetic field. And anchored fields have fields that takes the flux out of the domain. So he found a way of describing the incomplete magnetic linkages, okay, by referring the linkage that you calculate to a very unique potential field, which is defined by the magnetic field that you have spreading through the boundary. So there's a boundary flux that defines this unique potential field. So I came so much later. Mitch Berger was my second postdoc at HAO. I bugged him and I bugged myself. Once you have established that the relative helicity is physical, okay, then it must be fair to say I can define the relative helicity without involving the vector potential. Because I'm not obligated to describe the magnetic field as this way, V is to the curve A. And therefore, physically, I should be able to find a way to redefine relative helicity in physical terms without having to worry about the vector potential and gauge invariance. And I managed to do it in 2011. That's very important for me to do and for everybody to do, because you need to have a rugged measurement of what magnetic twist is to be able to talk meaningfully about the hemispherical preference for helicity of one sign in the north and helicity of the opposite sign in the south. Well, having come this far, I decided that the mathematics about that is going to take me very far away from what I'm doing. Well, I've achieved one thing for the talk, namely, you can, if you really want, make it very quantitative as to how much helicity is lodged in the magnetic structure. So from there, then you can say, you can quantify the horror of accumulating too much helicity if there were no CMEs. So now let me run through a number of interesting observations. Here is this remarkable prominence that I've located in the Big Bear H alpha through this picture. This prominence is made up of pieces of prominence that run practically across the diameter on the face of the sun or of the chromosphere. And I have this red arrow just to let you know where this has rotated to. And each piece is taken out eventually by CMEs. And to be sure that we don't get fooled by these guys, so this is where Tom Berger and I got together. It was such a pleasure to have run into this guy. This is Yoko. You know, if you look at H alpha, look at this sheet of prominence, you can't even imagine what the geometry of the sheet is. But H alpha is constantly draining down and is a hanging curtain shaking away. So that is what prominence actually doing. So as to the time-dependent part, I'm not going to draw into on it now, but later on, I have to come back to address this thing here. Okay, so the next slide. Okay. So let's go back to the cartoon sketch because life is easier without having to deal with 3D. But we captured enough. So the magnetic field exerts a magnetic pressure. And as we know, there's also a magnetic tension force. And it's wonderful if the tension force can confine the magnetic field. Then we can have a magnetic field which is, say, force-free. And that was where fusion research started in the 1950s. Can you build yourself a force-free magnetic field and you've got this little pellet right at the center that's compressed to such high density that fusion will take place? So Chandrasekhar came along with a theorem. It says that the tension force can act in a certain correct direction to confine a high magnetic pressure, but it never could succeed because intrinsically the magnetic field must expand. Okay, so that's the first point to realize. Then the the three-part corona helmet can be viewed in terms of the following. There's magnetic tension force, which is this part, and there's magnetic pressure where the field is strong, which is this central region where the flux rope is, and then there's gas pressure along each field line. Okay. And this flux rope here is actually held down by gravity. It's a combined gravity of weight of both the high density shell as well as the weight of the prominence. And then when confinement fails, because gravity wasn't able to hang it together, then the helmet leaves. And actually, mind you, the helmet can leave at a range of speeds from 2 kilometers per second under certain circumstances to as high as 1,000 kilometers per second. The anchor part of the field after the CMEs left will be open with a thinning current sheet in the magnetic equator, which then reconnects and produces to 2 ribbon flare trapped in the reconnected part of the magnetic field. So this, I think, not every flare is like that, but those flares that are related to CMEs are of this nature. And it is a CME that causes the flare. Because if the CME didn't leave, then these open field lines would not be reconnecting to produce a 2 ribbon flare. And that was a very interesting time in my life as well as Ionosphere's life, because I ran into the flare people. They didn't like the flare to be, less than the prima donna of the scenario. Okay, and it's all very emotional. but I think the case is very clear. Okay, so let me go on to tell you something else that's very interesting that HAO is very proud of. Mauna Loa. All the coronagraph that you have in space, don't look at the inner part of the corona for all kinds of technical reasons. Okay, you want to catch the dimmer part of the corona and so on. Okay, and if I forget, remind me about SOHO. Very interesting point, which Russ Howard confirmed for me. But anyway, so in this field of view, this is about 1 solar radius to solar radius. Mauna Loa has a monopoly of seeing CME taking off. And when they first built this instrument, Dick Fisher and I were sitting together in the conference, and I said to Dick, I was doing some calculation. If the CME start off dark rather than bright, then that would make life very easy for me to explain what's going on. And his jaw almost dropped because his instrument had just been deployed. And together with Dick Monroe, they found a dark thing coming through that became the CME. So this set of successive images was given to me by John Burkhardt, and you can see what a CME looks like in this region. And out there, then it became this 3-part CME. And this is so amazing. This is the size of the sun. That's occulting this, of course, it missed completely the 1 solar radii, bottom layer of the corona. And this will correspond to that. And the reclosing of the push open or kept open, left behind open field, the reconnection then produces the flare. And then once the field reconnects, then there's a trap region of the bipolar field that traps the hot gas of the plasma. And mind you, that plasma cannot conduct its electricity, cannot conduct its thermal energy across the field line. Keep remembering that magnetic fields are perfect insulators. And this is a lower temperature movie of the ongoing two ribbon flare seen from the top. I think like, where am I now? Here. And it's just so spectacular. So as it reconnects, it would more and more of close field lines, the foot points spreads wider and wider. And then, the next picture came from Homburger. And this is just a point. I hope I make it okay. This is a point about the CME mass, 115 grams, is significant gravitationally speaking. In other words, gravity is part of the problem. And of course, gravity is part of the problem. The helmet streamer is held in with its flux loop by the weight of the prominence as well as by the shell, the bright shell over the flux loop. So like a hot air balloon, if you want this thing that holds everything down to let the CME out, you got to dump some of it. So this movie, across, I think, several emission lines, okay, including the very cold ones, is, for me anyway, the first CME I see where the cold material actually gets thrown around and falling back down. Now, all that you can fault me for saying that I'm not quantitative. I didn't do the modeling, but I think this is very telling. So maybe we should estimate how much mass is involved in holding the flux loop down. Okay, and so the dark color will be the absorption of the colder material in this CME development. So I'd like to conclude with two fundamental questions, and I still need some time. Let me try my best, okay? There are two fundamental questions that all these things shows. One will be, how might one characterize the failure of gravitational confinement that produces a CME? Those are the dynamics of it. And then the other one will be something that I postpone all the way to the end, if I can have time for it. What is the nature of the magnetic heating that ubiquitously and unfailingly maintains a 1,000,000-degree temperature? Bearing in mind that temperature thermal flux cannot be conducted easily, say at least by the electrons, across magnetic flux surfaces. So here is a very important scaling law, and that's where the polytrope really is very useful. If you have a homologous sphere of expanding, that means it's expanding without changing too much, then density, the mean density is going to drop at 1 over r cubed. If you take 1 over r as your gravitational potential of a central object, then W times the density, the gravitational potential energy density is going to scale at r to the 1/4 up to r to the 4th power. Magnetic field is going to scale as r squared because it's conserving flux, and therefore magnetic energy density is going to scale at r to the power -4. And therefore, gravity and magnetic field, they go hand in hand. They scale very well. In other words, gravity can hold a field down. And if it doesn't hold it well enough, the magnetic field will go off. And it will take the mass along with it because they both scale similarly. So you would expect a certain scaling property that allows this structure to expand at almost any speed. Then comes the pressure. There is a polytrope. If you set the polytropic index of 430, then the pressure also scales the same way. And that was how I've discovered I can have a closed form solution for a CME strong for a polytrope with an index of 430. The thing that took off for this or excitement is that in 1995, Bruce Light led a whole bunch of us. In studying a full set of observations. There's a delta spot, a sunspot that was going across the surface of the sun. And the observation was complete, as complete as was possible with all the instruments. And they were able to come up with that, and I was asked to participate. Then I thought of something. Look, a delta spot is a pair of spots that didn't obey the HAO-Nicholson law. The HAO-Nicholson law says that in every solar cycle, if the leading spot is south north, then each pairs of spots tend to have the same south north in one hemisphere in the opposite direction in the southern hemisphere. And here and there are the outlying ones called the delta spot where the polarities split around. This indicates that the field comes out this way. Therefore, none of this field line is ever going to come from this side, and the field is going out the other way. So this guy is completely disconnected from the surrounding. So it is really like a closed magnetic field. And what can be a closed magnetic field? A spheromag. A spheromag is simply a twisted field of, say, a ball, such as sketched around here, and it's self-contained, and it's just a superposition of two fields, one a toroidal field that runs out and spills around, and then the toroidal field which is twisted and going around. Okay, so I had always thought that this damn thing is the flux tube of a prominence because it's a rod, and that's what everybody thinks of. Very few people, maybe they did. I don't know who they are, but I thought suddenly, my goodness, this is also a rod, the one right at the axis. And so if I turn it around this way, then I would have a horizontal rod, but my field is very complicated. So if this thing were to sit above the photosphere this way, then this will be the field lines that goes into the shell, and this will be the prominence tube. And I have to give credit. This is a very recent publication, 2020. They gave this beautiful picture, so I took it from them. You know what they were studying? They were studying the application of spheromags to intergalactic medium. I mean, my God, how far can you go? But anyway, I took that stuff, I twisted it around, and I squeezed it this way, and that agreed so well with the observations. And Paul Seagrave, associate scientist, was working with us, was the one who took the field and showed that if it comes true, then you've got these white lines which corresponds to this axial field. And wherever the white line has a bow downward, because it's red in color, and it looks rather like a prominence. So this is the structure where we have a realistic three-dimensional geometry. And then I ran into Sarah Gibson, and she gallantly went through the mathematics with me, and then we calculated. The light et al. Delta spot field can be transformed into an exact solution of the full set of MHD equation for gamma equals to 4/3, and it would take the puzzle of the field. So this is actually the cavity itself, and that's your prominence. And then out here is the shell. They'll go, and Sarah had a great time coming up with all the graphics and taking, that led me on the way. Okay. So I got 5 more minutes. There's a parting question that was the reason why I came down to look at all this again. Scott McIntosh and I got together over 3 years ago, and then I found something very nice as a solution. But I couldn't get it published. I kept questioning everything I had, and I went this way. So this is very provocative. The delta sunspot, by its topology, intrinsic topology, is a closed flux system. And if it comes true as T-Graves graphics show through the photosphere, then the solar dynamo may actually create flux systems that are detached. And if they're detached, then there will be instance of such a thing. And it actually not only made its way into the corona, it made its way all the way out into interplanetary space as a CME. So this part is the Unhausen summary of the properties. There are 2 points to make. One, the coherent liftoff of three-part helmets structure accelerating high speed, any speed in fact, suggests is the characterization of the dynamics of a CME. I mean, it's never going to be self-similar because the pressure has a role to play and it may not be a quarter gas by doing it. So that part is a good point to make. But there's a very provocative thought. You see, it has to do with the fact that the mass loss is 10 to the 12 to the 13 grams per second, and the CME only took care of something like 10%. Is that so insignificant about this number? It is not. The reason it's only 10% is because it actually came from a helmet streamer, a helmet itself, that actually suppressed anything to flow out. And that's why you hardly see any mass to be contributed by CME, except from those regions where a helmet streamer actually sits. But the prominent movie, this is a Newton for me now, that it is highly dynamic only because if you think of your cavity and the helmet streamer, it is not static either. Why should anything be going on there? You see, there's a quasi-static emergence of flux into it. And as it expands, the siphon flows of all kinds, and they can't flow right simply up into the atmosphere because the magnetic field is very complicated. And then it gets agitated by the surrounding. So the siphon flows cause flows in the complicated magnetic field, and it flows all over the place, including across field lines. And how could that be? Okay. But anyway, this is where I think the direct simulation for both radiative transfer as well as MHD would be a worthwhile thing to do. So this is my last slide. Okay, so can I just take 2 minutes? I can't deal with the ubiquitous spontaneous current sheet that Jim Parker was talking about, but I had the great pleasure of writing a review of it published in 2023. The point he was making was this. Some part of it, he gets very rigorous. He was able to show what he was talking about. But Jin is not about mathematical rigor. He's about, you see, his calculation goes like this. He first has a forethought, and then he does a calculation to see if he was wrong. And his forethought will guide him into how he might prove himself wrong as a first goal. And then when it was not wrong, then it reinforces what he was talking about. So to make a long story short, what he's saying is the following. If you look at a sketch that he had, where these fields are twisting around, locally you're looking at a foliage of flux surfaces pushing into each other. And remember, your Lundquist number is so large, it's practically frozen in. If they push into each other, the blue flux surface can give way, and then these two other flux surfaces push their way through a hole and come into contact, and that's a current sheet. And like hell, how could you think that with high conductivity at frozen condition over macroscopic scale, this doesn't happen? So that's point number one. The second point was a blind spot. I think I spotted this blind spot. There was a meeting. Okay. We like to think when the exact neutral point, when you push on the two sides, you will squeeze the neutral point this way, and you got a current sheet, and that's how reconnection takes place. But there's a blind spot. This is a planar field. All these have a third component out of the plane. When you squeeze in the neutral point, it will spread out this way. But all these lines that separate all the different fluxes are also tangential discontinuities because they are responding to the different respective connectivity. And tangential discontinuities occurs here. And Sierovatsky in 1972 had a paper, we have a brilliant statement. He says that if you have a twisted field, if you know how to slide appropriately, you're going to find this configuration anyway. And therefore, this should come in very regularly. And then the last point is something I also realized to help myself. You see, the Lorentz force is made up of a tension force and a pressure force. The tension force depends on the curvature of the field lines. So the Lorentz force actually lies in oscillating plane. I first learned this in college. The oscillating plane is if you have a field line space and you take a point, you can define uniquely where the tangent is. And then you can define where the normal to that line is. Together, they define the oscillating plane. So the Lorentz force sits in that plane. So the tension force. So the tension force lies in the plane. And if it's just balanced, the magnetic pressure is a gradient in a three-dimensional surface. And these two are so anisotropic and so distinct. If you live in a two-dimensional world, that is fine. You just this plane and everybody seems to know their places. But in a turbulent field like this plane isn't going to agree exactly with the normal or the gradient of your iso pressure surfaces. And that's the nature of all these, okay? All this formation of tangential discontinuities. So discontinuities comes not just through special places like the discontinuity between the flow of your solar wind and the helmet bound or the helmet, and the discontinuity is unavoidable at the boundary. But it actually forms very, very readily in the magnetic field, and that perhaps is the origin of coronal heating. Not saying that you know exactly how the heating takes place, but how inevitable it is for Rosening condition to be regular rather than singular in its mathematical structure. All these things also led me to conclude, there's a satellite named after, or instrument named after Chandrasekhar. It observes in X-rays. One of the surprises was when you look at a place like the Orion, the stars all have corona. And if you believe that you have figured out enough of the coronal physics, then you could say that the heating of the corona, the Parker current sheet, is a universal process. And therefore, coronae are a sort of universal astrophysical phenomenon. And so I think that's a good point to put it. But I have to also add this. When I was a graduate student, something that Enrico Fermi said and was saying with the department for years, especially to the graduate students, if you want to give a good seminar, you mustn't forget that the audience will always have the pleasure of listening to something familiar, And I would say there's more to it than enjoying familiar ideas. Many of these stuff that I talk about are familiar by now. Is that when you take all the familiar ideas and put it together, very often something will jump out at you. And what jump out at me is really that the corona helmet, as well as the cavity, is not a static thing. It's been bombed left and right by the surrounding. And it is also growing and breathing, sometimes expanding, sometimes closing. And the bottom, the base of the solar corona, is where mass flux exchange is taking place. So with that, thank you very much. I'm 7 minutes over time.
Questions?
I'll ask a question. Thank you, BC. That was lovely to hear how familiar but new at the same time. So the question I have is, you talk about heaving. Can you say a little bit more about what you mean by heaving? What is doing the heaving? Is it the provenance material or the Linderby material?
So let me go back. Yes, and actually, the term heaving came from Jim Parker. I mean, the guy has so many things he did, so it's hardly surprising it came from. So here. So here is your solar wind flow, close to static equilibrium down below, going up with such high speed as to hit the sonic point, become supersonic. But there's a mass flux in there. So down below here, even though you're close to equilibrium, that mass flux is in. So the corona doesn't know that there's a solar wind, because anything, even if you put a rock here and interrupt the solar wind, because you're in the supersonic region, so that disturbance never could be communicated down below. But down below, all it sees is that every time I try to fill it up with hydrostatic atmosphere, it just gets taken out. And therefore, the lower atmosphere, actually, this was adjective, it was heaving outward, And if, for example, if you have an instrument and you were sitting, say, in the low corona, sitting there and observing everything, you discovered actually you could measure a mass flux at any level, and it's just sort of going out. So it's like, it's heaving out. And sometimes the wind may fail for some other reason, then it will come down. And what I am saying now is that in the helmet streamer, here, clearly there can be no heaving because it's not having a constant mass flux going out of the region. But it can do many other things. Namely, this volume is actually like a balloon. The magnetic field over it, the magnetic flux over it, is keeping material from going out. But as soon as the surrounding changes, it starts to wiggle and push around. And as prominence starts to drain through, the mass that's holding part of the flux through is also disappearing, and so the flux through will rise up. So there's all that going on, and it's just not necessarily in the sort of explosive manner like a CME. So that part is what I realized that, if I could persuade people to build instruments, I would say build something that you could say after 2 days of observation, the total mass in this volume has changed. And what happened to it is just this trapped volume before it becomes a CME adjusting itself. So this is the part I say that, looking at familiar thing, well, we enjoy it. Very often they tell you that you didn't quite catch the whole thing,
Other questions? Anyone from online?
Thank you, BC. BC was a mentor to me like you wouldn't believe. I mean, I remember in the early 90s when I first arrived as a postdoc and a junior scientist, we were very fortunate. There were 5 positions offered to people like myself, and 5 were filled. I'm the only one left, which is kind of interesting. It tells me, oh, all the really good people have left, and there's just me stuck here now. No, but the point is that BC opened my eyes to a way of thinking, and in particular, the notions of things like constants of motion related to different things like the topology of the magnetic field, the meaning of the Parker problem. I mean, I thought the Parker problem was pretty straightforward until BC pointed out to me that, there were things like Ard van Bellinghoyen, who'd supposedly shown a proof that tangential discontinuities couldn't make it down all the way through everything. And so there was something wrong with that picture. And then BC illustrated that very simply by saying, well, if you look at it very carefully, what you'll find is that Ard, clever guy that he is, he basically generated an algorithm for making smooth solutions. So you couldn't actually say anything about the non-smooth solutions. And I really take your point very well that the putting together various bits of physics and various bits of mathematics and coming up with a sum that's much bigger than the components of each one.
That's a part that
That is the thing that I think you uniquely have shared with many of us in solar physics that I have rarely seen elsewhere. And so I want to thank you for your patience. I mean, he had a lot of patience working with me early on. I mean,
no.
I was bashing my head against the wall for a long time.
You haven't mentioned the counterpart to all that. I benefited through the years of association with you.
We did work on different things, but ended up talking about some really fascinating problems together. And I really miss you, BC. And it's been, a privilege to know you. And I think if people ignore what you're saying here, they're going to ignore it at their peril.
Well, so I should put a perspective on, say, the work by Van Bellinghoyen and others. It was very difficult for them I believe that's my interpretation of, I mean, Art and I could talk to each other, so we're not having happiness. I think they honestly could not accept the Parker theorem. Okay. And at some point, I kind of take a tangent off. I really didn't want to figure out. But I could say this much, namely that our profession is such that we also get funding. We have only so much time. So people never address those issues. But what I'm setting out to reply to you is, some of them are very bright, including Art.
Oh, yeah.
And they come up with counter proof of the Parker theorem. And were really not so easy for me to sit down and say, no, they got it wrong. I even have a very brilliant, established scientist above my generation who actually came up with a proof that Parker could not be right. And he sent it to me. He said, BC, take a look at this. But Rich Wolfson and I have already settled the issue a long time ago. So it was so easy for me to immediately write back and say, no, this is where your proof went wrong. But all that sharpens our understanding of the theorem. So to talk about something more, less contentious, but very far-reaching is the following. Take the homograph cascading of wave numbers from small wave numbers at larger scale to high wave numbers as a model for turbulence dissipation. So viscosity is very small. So the cascade brings a large scale structure, the small scale, so that in the small scale, then viscosity takes over, and that's where energy, and you can have good scaling laws. Okay. Now, they're talking about ideal fluids. If for ideal fluids, there's a crazy conservation law, just like frozen condition, your vorticity is frozen in there. Okay, so this hydrodynamic turbulence cascading away until you get to a region where viscosity is important, the done vorticity is conserved and frozen in. And the frozen in condition was what caused the origin of the current sheet. And therefore vortex sheets form. And once vortex sheet forms, then you actually don't have a bloody cascade, see? Because you've got a real headed of a nonlinear problem of the vorticity. And I searched around, and I found two very smart guys who did the following calculations. So for those of you who like this, you should go and look at what they did. Now, I can't remember their names, so this is my old age. Okay? So, you know what these two guys did? They took the classical result that what do you go for it? Helmholtz-Kelvin instability. Okay, it's unstable, and they took the calculation from the linear regime to the first encounter with the nonlinear regime, and they found that the calculation showed them that the evolution becomes singular in time.
Oh,
So I think they ran into the vortex sheet.
Mm.
But here you see, all these things are all over the place. Sorry, I took up too much time, but
Okay.
Delightful. Thank you very much.
Okay.
so thank you for coming, and thank you for watching from remote. I didn't know that our colloquium has become through the internet.
half and half.
Okay, let's thank our speaker again.